Hello there. Welcome back to Differential Questions by Alex. This is me. All right, so today we're going to continue again the second order linear differential equations, but we're going to focus on the idea that we are only dealing with homogeneous equations. And moreover, we're going to focus on the superposition principle. Okay. And so let me give you the outline that I gave you last time. So again, this is just one section, and then this section is about just talking about what do we mean by second order linear differential equations. And we talked about existence uniqueness last time, okay? But now today we want to focus about homogeneous differential equation. And then just for today, we are only going to focus about the principle of superposition. And so I'm giving you an outline because it's a lot of information just for one section. So this entire thing is just one section. So all these definitions, and I'll try to break it down into pieces. All right, so let's talk about principle of superposition. And what it means is the following. Suppose that you have a homogeneous differential equation. So homogeneous, this means that this is a zero here on the outside of the equal sign. And so suppose that we have two functions that are a solution to this problem, okay? And then just a little comment here. Notice that here I have not put any initial condition, okay? So when you put the initial conditions, that's like a full problem. And then you want to know whether that problem has only one solution, zero solutions, or many solutions. Here we are only dealing with the differential equation. So we are ignoring the initial conditions and we're just dealing with the differential equation. And so here we're saying that if we have two solutions to the differential equation, then the combination of the y1 and the y2 will also be a solution to the differential equation. Okay. So what that means is the following. Suppose that I differentiated I have my solution that I have as my combination. Suppose that I differentiate that function. And suppose that I differentiate it twice, actually. And I put in my a function, my b function, and then this is my c function. So don't confuse this c with the little c that I have in my notation. Okay. And so if you differentiate once and twice and plug it in into your differential equation, the output would also be equal to 0, because initially y1 and y2 individually, when you plug it into the differential equation, they do give you 0 at the end of the day. All right, so let me give you some examples. Actually, let me give you one more slide here, repeating the same thing. And so what we're saying is this: if you are already given two solutions to the problem, to the differential equation, then we call this a family of solutions. Okay, and so here we are free to choose the C1 and C2. Okay, so you can have y is equal to 2y1 plus 3y2, or whatever numbers you want for C1 and C2, and then that will be a different function, same format, but just different numbers in front of the y1 and the y2, and then that function you can plug it into the differential equation, and then it will be equal to 0, as long as the original y1 and the y2 are solutions to the homogeneous equation. All right, so just a little bit of terminology here. So this function that we have, the linear combination of the y1 and the y2, this is also called a two-parameter family of solutions, and then the number c1 and the number c2, they're called the parameters, and then that's what we call it, a two-parameter family of solutions. So we don't have just one function here, we have infinitely many functions here because we're free to choose whatever the values we want for c1 and c2, and then this function does satisfy the differential equation. All right, so a little bit more terminology. The same function is also called the general solution to the homogeneous equation. Okay. And then also one more other piece of terminology. This same function later on, it's also going to be called the complementary solution, but it's going to be called the complementary solution to the non-homogeneous equation that has this format. Remember, right now we're dealing with a homogeneous equation. Later on, we want to deal with a non-homogeneous equation. And so my wording here is not exactly precise, but I want to kind of introduce here the idea that the yc function is also called the complementary solution to the homogeneous problem related to the non-homogeneous problem given here at the bottom. I'll say more about this later in a different section. Right now, I just want to tell you that we call the same function yc by so many different names. All right, so now a type of question that you might have is, verify that these two functions are solutions to the differential equation. And so what that means is that if we were to plug in the y1 into the differential equation, do we get that to be equal to 0? Well, let's do the check here, okay? So the y1 function is e to the 3x. The first derivative is 3e to the 3x. And then the second derivative of that function is 9e to the 3x. So if we were to plug it into the formula, so y double prime minus 9y. So let's plug it in, where we get 9e to the 3x minus 9, and then the original y function is e to the 3x. We plug in the y1 into the formula, and then we get this, and then you can see that this is equal to 0. So this is equal to 0, and so that means that the y1 does satisfy the differential equation. So y1 satisfies the differential equation. Actually, let me put it in blue to make it a little bit more positive. All right, so now we go to the next function that's given to us, so y2. So we have the y2 function, and then that's e to the negative 3x. And then the first derivative of that is negative 3e to the negative 3x. The second derivative is positive 9e to the negative 3x. And then we want to plug that into the left side of the equation, y double prime minus 9y. So plug in the solution, the y2 function, then you get 9e to the negative 3x minus 9, and then the original y2 function is e to the negative 3x. And what do you know? This does give you 0. All right, so that means that the y2 solution, the y2 function, this function that we're calling y2, is also a solution to the differential equation. Okay. So that's what it means for us to verify or to check that the y1 and the y2 are solutions to the differential equation. All right, now that we have checked that y1 is a solution to the differential equation and y2 is also a solution to the differential equation, and then this is a homogeneous equation. There's a catch here. This is a homogeneous differential equation because we have 0. Then the superposition principle. Some people call it superposition principle, some people call it the principle of superposition, doesn't matter, same thing. So this principle tells us the following: if you have y1 and y2 to be solutions to the homogeneous equation, then this new function that I'm going to create, which is going to be c1 y1 plus c2 y2, this is also going to be a solution to the differential equation. And then if I put in the specific numbers here, so this is c1 e to the 3x plus c2 e to the negative 3x. What I'm saying is that this new gold function, and then notice that this is not just one function, this is infinitely many functions because we have different values for c1 and any value for c2. So no matter what c1, c2 value you put in for there, if you use the gold function y, its second derivative, if you put it into the differential equation, it will be equal to 0. So this gold function is also a solution to the differential equation. That is what the superposition principle is telling us, or that is what it allows us to conclude. So that's a good thing. Okay. So that means that if we do have two functions that we know that satisfy the differential equation, then we can create infinitely many. And so this gold function here is not just one function. This is actually infinitely many functions because we have different values for C1 and C2 that we can choose from. All right, so that's just to help us get comfortable with the idea about the superposition principle, but also about verifying that the functions are solutions. So let me do the process up again. So we have a y1 function and then a y2 function, and now we have a different differential equation. And then again, this is a homogeneous differential equation. And so first we want to verify that these are solutions to the differential equation. And so let me just do this a little bit quickly. So this is e to the 2x, and y1 prime is 2e to the 2x. y1 double prime, this is going to be 4e to the 2x. If you were to plug in these three pieces of information into the left side of the equation, then it will be equal to 0. You can do the calculation if you wanted to. So let me just write it up, and then you can do the algebra. So you would write down 4e to the 2x minus 9. The second derivative is 2e to the 2x plus 14 of the original function, which is e to the 2x. So let me just underline a few things here, and I'll put this in blue. So the y double prime is here. So y double prime is there. This is the y function, and then this is the original function. All right, so you do the calculation, and then this will be equal to 0. Okay. Now the same thing is going to be true for the second function. So I won't do the calculation. I'll just tell you that you write down your e to the 7x, you write down your first derivative, write down your second derivative, which is not difficult. Actually, let me just do it here. 7e to the 7x, and then 49e to the 7x. And what we're saying is that if we plug in these three pieces of information into our differential equation, into the left side, it will be equal to 0. Okay, so you can double check. There'll be a check for you to do. And so now that we have those two pieces of calculations, we check that the y1 is a solution to the differential equation, and y2 is also a solution to the differential equation. And again, this is a homogeneous differential equation. And so the principle of superposition tells us that if we make the following combination, c1y1 plus c2y2, then this new function, which in this case it's going to be e to the 2x plus c2e to the 7x, if we look at this specific linear combination where we are free to choose the c1 and c2, so we have infinitely many choices, then for any c1, c2, this gold function will also be a solution to the homogeneous differential equation. That is what the principle of superposition is telling us. This gold function is also a solution to the homogeneous differential equation. All right, so that's all I have for today for this idea about the principle of superposition. And remember, I'm trying to kind of organize the thoughts here. We're dealing with homogeneous equations, but under this category, right now we just talked about the definition and then try to get comfortable with this idea of principle of superposition. The next topic is going to be linear independence. Okay, linear independence. Again, it's still talking about homogeneous equations, but we want to talk about linear independence, but that's going to be for the next video. All right, thank you for watching, and I'll see you in the video for linear independence.